Hello, everyone. Thanks for coming. My name is Carson Wang. I am from Intel. Today, I'm going to share with you the optimization we did in SparkSQL called adaptive execution. This is today's agenda. So first, we will discuss some challenges in SparkSQL high performance. And then I will introduce the background and the architecture of adaptive execution and how adaptive execution can address all the challenges. Finally, I will also share the benchmark result with you. So let's get started. So if you have been running SparkSQL, you know there's a configuration for the shuffle partition number, which by default is 200. So this is usually not enough for in a large data scale. And suppose you request a few executors and each with a few cores. So totally you have you have a few cores that you can use for this query. So for each reduce stage, it actually needs to run the tasks in a few runs, which equals to the partition number divided by the total core number. So to get the best performance, we usually need to tune the partition number a few times. And here is a challenge. If we set this too small, we may encounter some issues like data spill or even OEM. So data spill means that the data, Spark has not enough memory to handle that. So it needs to spill the data to the disk and read back again. So this involves additional disk write and read. So this will definitely affect the performance. However, if you set that too large, this means more scheduling overhead and also more I/O requests. And some customers also complain to me that in the last stage, they cause too many small output files. So during our benchmark, we usually start with the partition number from the core number and from C to C and so on, and until the performance begins to drop. So this way to find the best partition number. But in production environment, this is usually impractical. So this means that many queries actually don't run at the best partition number. And here is the second challenge. We know currently the same shuffle partition number actually doesn't fit for all stages. And during the execution of the SQL query, the shuffle data usually decrease. But however, we can only set one shuffle partition number. So this leads us to think about the question, can we set the shuffle partition number for each stage automatically? We will answer this shortly. So now let's take a look at the second challenge. We know the core of the SparkSQL is a catalyst optimizer, and it analyzes your SQL or your data set program and to logical plan, optimize that, and finally get the physical plan. So the execution plan it selects is very critical for the performance. However, at the planning phase, it's actually not easy to get the optimal execution plan. But at runtime, we get more runtime metrics like the data size and the row count. So it's possible that we know at runtime there's a better execution plan for better performance. But currently, there's no way to change the execution plan at runtime. Let's take a look at the join selection as an example. So in Spark, we know there's two typical join types. One is the broadcast join. So in this case, the smaller table is broadcast to each executor. And then this only requires one map stage. So each map task reads a partition of another table and join with a smaller table. So this is very efficient. And another join type is shuffle hash join or sort merge join. So in this case, it involves two stages. The first map stage reads the data and shuffle writes the data to the local disk according to the shuffle partition number you set. And the reduce task needs to fetch the data from all the map output and perform the join. So this involves a shuffle phase. So now in SparkSQL, currently there's a broadcast threshold we know, which is by default 10 megabytes. So this is used to control if we use a broadcast join or a shuffle join. However, for some complex queries, we know a join may take some immediate results as input. So at the planning phase, SparkSQL doesn't know the exact size and probably still plans it to using sort merge join. Here is an example, and we can see from the metrics of the exchange, the data size of one import table is only 600 kilobytes, but it still uses a sort merge join. So at runtime, we know that the table is small enough for broadcast. So this makes us think about, can we optimize the execution plan at runtime based on the runtime statics? The third challenge is data skew in join. We know this means that data in some partition are extremely larger than other partitions. So this is data skew is a common source of slowness for shuffle joins. And here is an example. We can see most of the tasks finish in just a few seconds, but the slowest one needs about 4 minutes to finish the task. So currently, there's some ways to handle skewed joins manually. For example, we can try to increase the shuffle partition number so the data maybe will be hashed to different partitions, or we can increase the broadcast threshold to wish that the shuffle join will be a broadcast join, or we can even filter out the skewed keys and add some random prefix to that. So all of these methods involves many manual effects, and actually is very limited and cannot work for all the cases. So this leads us to think that can we handle skewed join at runtime automatically? So all these challenges makes us to think about a new adaptive execution mode in SparkSQL. So here is some background of this feature. Early in 2015, Matei and Huayin from Databricks, they have already done some initial work in this area. So I listed some JIRA here. And the most important one, so now the second JIRA added support to submitting the map stages individually in DAG scheduler. So we can now submit a single map stage. And the third JIRA also tried to add an exchange coordinator to automatically change the shuffle partition number in the reduced stage. But currently, this is some limitations because sometimes it adds some additional shuffles. And also for some cases like three-table join, it cannot add the same exchange coordinator to all three exchanges. So based on this work, we try to make a new design and also add some new features. So here is the new adaptive execution architecture we designed. Suppose we have an execution plan to join two tables, which is a sort merge join. In SparkSQL, we know each operator is a transformation of the RDD. So from this execution plan, we can get the DAG of RDDs. And finally, we will submit this to the DAG scheduler to execute. So in this mode, we know once we have the DAG, there's no chance to change the plan. So in adaptive execution, we divided the plan. Firstly, we will divide the plan into multiple query stages. Each time we see an exchange in this plan, we will add a query stage element to this tree. And we will, so the query stage represents a single execution stage. So, and we will also add a query stage import to this tree, which is actually is a leaf node to the parent query stage. The query stage import is used to hide the child stage, and it's also used to create a shuffled low RDD to the parent stage. So after this transformation, we can, in this example, we will get 3 query stages. And for the last query stage, it is a sort merge join, and it has 2 query stage import. So when we execute this query stage, firstly, we will execute the child stages concurrently. And we will wait for the completion of all the child stage So after that, we got all the metrics of all the child stages, like the data size, the row count. So we know, for example, in this case, we know one of the table is small enough, which is only 5 megabytes. So we can, at runtime, we can optimize this plan and change the sort mode join to a broadcast join. And finally, we can also change the shuffle partition number in this case. And finally, we will generate the DAG of RDD of this single stage, and then submit this stage to the scheduler to execute. So this is the overview of this adaptive execution, the architecture. And now we will revisit all the 3 challenges we discussed and see how we can address all the challenges. So the first one is to set the shuffle partition number automatically. Suppose we have 5 initial reduced partitions with size 17 megabytes, 30, 20, 10, and 15 megabytes. So initially, we need 5 reducers to do this work. But if we set a target size per reducer to 64 megabytes, at runtime, we can actually use 3 reducers. So for the second reduced task, it will read the 3 continuous blocks, which is partition 1 to partition 3. So in this case, all 3 reduced tasks handle almost the similar data size. And we also did optimization in this case. So when it reads the 3 continuous blocks, it will actually read just like a single block. So this will greatly improve the I/O performance. And another thing is that we noticed that sometimes the data size is very similar, but sometimes the row count could be very different. So we also add a support to set a target row count per reducer. In this case, we can change the number of reducer at runtime automatically to fit the data size for this stage. Now, the second one we support now is to optimize the execution plan at runtime. Currently, we support change shuffle join to a broadcast join when we notice that one table is small enough for broadcast. But we know that the output distribution of shuffle join or a broadcast join are very different. So sometimes this will cause additional shuffles. So in our design strategy, we don't want to add additional shuffles. So let me just look at 2 examples. This is an example of 3 table joins. And at runtime, after we executing the child stages, we know the data size of these tables. So here we can see that table 1 is smaller than the broadcast threshold. So at the first look, we can change join 1 to a broadcast join because table 1 is small enough. But if we change that, it will cause, we will have to add another exchange operator between these 2 joins because sort mode join 2 has a special requirement, the distribution requirement on its children. So in this case, we will not change that. We will not change both joins. And here is another example. So in this example, both table 1 and table 3 are less than the broadcast threshold. So in this case, first we can change sort mode join 2 to a broadcast join because table 3 is small enough. And after we doing that, the broadcast join has no requirement on the left, has no distribution requirement on its left child. So we can also change join 1 to a broadcast join. So the rule here is that we do not want to add any additional shuffles in this single stage. So we will only change that if that will not cause additional shuffles. So what's the benefit of changing a sort mode join to a broadcast join? We know the data has already been shuffle right to the local disk, so we still need to shuffle read this data. But but the difference is that in shuffle join, suppose we set the shuffle partition number to 5, we need to launch 5 reduced tasks to perform the 5 reduced tasks. So each reduced task will fetch the data from all the map output through the network. So when we, in adaptive execution mode, when we find that the table B is small enough for broadcast, we will broadcast that table. And now we will only need to launch 2 reduced tasks because there are only 2 map tasks of table A. So in this case, each reduced task will only will read the whole output of the one map output from the table A. And when we schedule this task, we can schedule this reduced task to the node where the map tasks run. So this will be actually a local read. There's no data will go through the network. So in this case, and because it also reads the data, the whole output, so it's a sequential read instead of some random read. So this will greatly improve the I/O performance, and we will also see more detail in the benchmark part of this. So the third challenge we mentioned earlier is the data skew. So with adaptive execution mode, we can detect a skewed partition at runtime very easily. So after executing the child stages, we know we can calculate the data size and the row count of each partition from the map status. And a partition is, we defined that a partition is skewed if its data size or the row count is n times larger than the median, and also larger than a predefined threshold. So suppose we are joining table A and B, and we detected that partition 0 in table 1 is a skewed partition. So normally, we need to shuffle all this data in partition 0 to a single task, and this will be the slowest task. So instead of doing that, we will use n tasks to instead of 1 task to join the data in partition 0. So each task will read only a part data of partition 0 from table 1. We use special, we actually update the shuffle read interface so to support only reading from a part of the map output. So in this case, we will finally, we will union all the join results, and this will avoid the shuffling all the data to a single task. All right, so finally, the most exciting part, let me share the benchmark result with you. Here is the cluster setup of our environment. We use 99 servers with each one is equipped with Intel Broadwell CPU. It has 88 cores and 256 megabytes RAM and 7 SSD. So the network is 10 gigabytes. And we use a Spark master branch, which is 2 months ago. So we run a TPCx 100 terabytes benchmark and compare the performance of SparkSQL and adaptive execution. So we found that many queries get the performance boost, like 20% or 30%, and the best one even got is three times faster. So this is really cool. And when we analyze all the benchmark results in more detail, we can see more why we can get the performance improvement. So the first one is auto-setting the shuffle partition number. So initially, we set a relatively large shuffle partition number, like 10,000. So in this case, we can see that we have 2 stages, and actually the data size is not very large. So they finish in 10 seconds and 18 seconds. And with adaptive execution mode, at runtime, we can automatically change the partition number to about 1,000. So we can see from from the image that the performance is much better and it's finished in just 7 and 4 seconds. Because this means that there will be less scheduler overhead and the less task startup time. And this also means that less disk I/O request because we can read the continuous partitions in a single request. And finally, we also observe that the shuffle write, the data shuffle write to the disk is also less because that more data are actually aggregated. So in this case, we got the performance improvement by auto-setting the shuffle partition number at runtime. I understand that it's possible that if you tune the shuffle partition number carefully in original Spark, you can get a better performance. But again, you can only set one shuffle partition number for this query. So probably some previous stages handles more large data. So it actually needs a large partition number. But for some other stages, the data will be much less. So with adaptive execution, we can automatically set the partition number for all the stages. This will fit for all the stages. The second improvement is changing a sort mode join to a broadcast hash join at runtime. So here I listed an example here, which is query 8. So this is a sort mode join to join 2 tables. And we can see that one table is very large, about 1 terabyte, but another table is only 2.5 kilobytes, which is very small. But Spark still plans that to a sort mode join because at the planning phase, it doesn't know the exact data size of the small table. So in this case, the sort mode join suffers from the data skew issue, and the slowest task finished in 2.5 minutes. So it takes a very long time to finish this join. With adaptive execution mode, at runtime, we know the data size of these 2 tables. So we choose to change this join to a broadcast join. So we will actually launch additional stage to broadcast this small table. After that, we will perform a broadcast hash join. So in this case, we can see we can finish this join in just 10 seconds, which is really a good improvement in this query. So this is because that we eliminate the data skew and the straggler in sort mode join. And we also, as we discussed earlier, we changed the remote shuffle read to a local shuffle read. And the random I/O read becomes actually the sequential I/O read because it's read the whole output of the map output. And another thing we can notice is that in adaptive execution mode, we actually did another optimization. So from this image, you can see we only read 17 gigabytes instead of all the 52 gigabytes data size. Because when we know that one table is small enough, and we also figure out that some partition in that table is actually empty. So when we do the broadcast join, there's no need to read these partitions from the larger table because this partition is empty in the smaller table. So we only read 70 gigabytes from when we perform the broadcast join. So finally, during the benchmark result, we also noticed that some scheduling difference, which is also sometimes cause performance improvements. So in SparkSQL currently, we noticed that it's hard to wait for the completion of all the broadcasts before you scheduling any map stages. This is because it needs get the broadcast variable when build the DAG of the RDD. So in this example, I set the broadcast threshold to 100 megabytes, which is not very large. And Spark, the actual data size of one table is about 600 megabytes. And at the planning phase, Spark estimates the table size because we only select a few columns. So it's estimated that the data size is smaller than the threshold. So it chooses a broadcast hash join. But at runtime, we actually read about 180 megabytes. And this, we know this is actually the data in a Parquet format. So this is highly compressed. So at runtime, when we read this data into Spark, which is in the unsafe row format, this becomes a 1 gigabyte data size in unsafe row format. So this is really actually become a big broadcast, even though I only set 100 megabytes as the threshold. But the data size actually is 1 gigabyte. So it takes about 19 seconds to catch the data to the driver, and then 24 seconds to build the hash relation, and finally 6 seconds to do the broadcast. So this adds up to 50 seconds. So this will be a gap between the broadcast stage and the map stage. So in that case, all the map stages cannot start because of this time. But in adaptive execution, we can submit the stage much earlier because as long as there's no dependency of this stage, we can just submit that. So we didn't observe such gaps between the broadcast stage and the map stage. So in such kind of cases, we can also see this performance improvement. All right, this is all for today's sharing, and thank you all. So any questions?
Thank you. We've got a couple of mics on either side of the aisle next to the camera. If you have any questions for Carson, please walk up to it and fire away. Make them short, make them succinct. No questions? Brilliant. All right, go ahead. Okay, yeah, that's a good idea.
Hi.
Hi.
Hi, thanks for the great talk. I was just wondering what the plans are around availability of this. I know that Intel has a lot of things like the advanced analytics platform and so on. Is this open source or available?
Yes, all the work we did at Intel will be open source. Currently, this is a POC at Intel, but we will also contribute this to the community, and we will have actually a detailed design doc. So welcome to discuss with us, and feel free to comment or discuss with us.
Great, thanks.
Thank you.
Anybody else? Oh, there you go.
Hey, have you guys experimented with map side joins which don't require any shuffle if the data sets are already bucketed and sorted?
Sorry, can you speak again loudly?
Could you repeat the question?
So have you guys experimented with map side joins which don't require a shuffle? So if the data is already sorted and bucketed, you don't require any sort of shuffling. Yeah, what we're trying to do is to change the shuffle join to a map side join. So in that case, we know so although you still need to shuffle read the data, but the data doesn't go through the network, you can just it's a local read. So this will be much better for the performance. So.
Okay, give a big hand to Carson. Thank you.
Okay, thank you all.